This is Shubhangi Rao. I am working as an assistant professor at MLR Institute of Technology, and I am teaching this subject electromagnetic field to second year EEE students. Today we are going to discuss about Gauss law and its application. Already in one of the lectures we have discussed in short, and today we will discuss about its proof and its application and the derivation. So let's start. So before going through the derivation, again let us recall what is Gauss law. Gauss law is the alternative statement of Coulomb's law, right? And this can be used to find out electric field intensity and flux density for symmetrical charge distribution. And this symmetrical charge distribution can be point charge, infinite line charge, infinite sheet of charge, as well as spherical distribution of charge. There are a few more points, like Gauss law is also used to find out charge enclosed or the flux passing through the closed surface. We should take care that whether the charge distribution is symmetrical or not. This Gauss law holds for any closed surface but can be easily applied to the symmetrical distribution. But one limitation is it cannot be used to find E or D if the charge distribution is not symmetrical. While selecting the closed Gaussian surface to apply the Gauss law, these two conditions must be satisfied. The first one is flux density is everywhere. It can be normal or it can be tangential to the closed surface. Normal means you can take theta is equals to pi by 2. Tangential, it can be taken as pi. So if this is the surface, normal. If it is like this, it is tangential. Like this, tangential. Like this, tangential. Right? So these angles can be theta is equals to pi by 2 or pi. So this d dot ds, it becomes d ds or 0 respectively. Second condition is d is constant over the portion of closed surface. For this, d dot ds is not 0. So these two conditions must be satisfied when we are applying Gauss law. Now let's see the derivation. Okay. So for understanding this, we have considered a point charge which is located at the origin of the sphere. Right. So we have to determine D, and to apply this Gauss law, we are considering spherical surface around this Q with its center as origin. This spherical surface is a Gaussian surface and it satisfied the previously two discussed required conditions. If you see, this is the surface, right? If you see, the D is always directed radially outward. This is D along AR. AR is the unit vector which is normal to the spherical surface at any point. This point can be here, this point can be here, anywhere. So this D will always direct radially outwards along AR. And here the radius is R, which can be taken as equals to A. Because this is a spherical coordinate system, we know the coordinates are r, theta and phi, where r is the radius which we have taken as r is equals to a. Theta is conical angle, this angle is theta, and phi is azimuthal angle. This phi is drawn from x-axis in anti-clockwise direction and its limit is from 0 to 2 pi. And this theta is drawn from z-axis in clockwise direction and its limit is from 0 to pi. So we are considering a differential area ds here, this one, this area, right? So we are considering this ds, differential area. The direction is normal to the surface, right, which is given by AR, and we are considering this spherical coordinate system, and already we have discussed that r is taken as equals to a. The direction of D is along AR, which is normal to DS at any point. Right. So, in this spherical coordinate system, this DS normal to radial direction AR is when we have to write it in terms of equation, we can write ds is equals to r square sine theta d theta d phi. That area will be equals to r square sine theta d theta d phi. When you simplify it, in place of r square, we can write a square, again remaining things are same, sine theta d theta d phi. Again we have to simplify this, ds can be written as ds an, where n is the unit vector. So ds is a square sine theta d phi and an is nothing but ar. Now the flux density due to the point charge will be given by this formula, d is equals to q upon 4 pi r square ar, where r is the radius, again r is equals to a square, so it can be written as q upon 4 pi a square ar. Then when we simplify it further, we use this formula, d dot ds is equals to mod d mod ds cos theta. This theta is the angle between d and ds. So mod d is equals to q upon 4 pi a square, ds is equals to a square sine theta d phi. Theta angle is equals to 0 degree. So we have to put it back to this formula. When we put it, we get this equation, q upon 4 pi a square, again here we have a square sine theta d phi and cos 0. So when you simplify it, a square will get cancelled, you get q upon 4 pi sine theta d phi. This is our third equation. One more way is there to avoid this confusion between the symbol theta. In place of that, we can directly write d dot ds is equals to q upon 4 pi a square ar, which is the unit vector, dot a square sine theta d phi ar. Again when we simplify it, we take this ar together, ar dot ar becomes 1. Then we again put it into the formula, it becomes d dot ds is equals to q upon 4 pi sine theta d phi. This is xi is equals to, we know, integration of d dot ds, surface integration of. Then we put the limits by using integration sign. The value of d dot ds is q upon 4 pi sine theta d phi. Now we have two angles, theta and d phi, d theta and d phi. So integration is with respect to this phi and theta. So in this integration sign, we need to put the limit of phi and theta. The limit of phi is, which is azimuthal angle, the limit is 0 to 2 pi, and the limit of theta is 0 to pi, which is conical angle. When we simplify it after integration, we get finally xi is equals to q, which is Gauss law, right? This is Gauss law, that flux enclosed by a closed surface is equals to total charge present on that surface. So this was the proof of Gauss law. Let us move to next topic. Use of Gauss law to obtain flux density and electric field intensity, right? So how do we find it? From Gauss law, we know that q is equals to integration of d dot ds. This formula we have already seen. Again, if we consider the sphere, the radius is r, flux density is d, which is in radial direction ar, always normal to the surface, radially outward. Let's consider that mod d is equals to dr. So this d can be written as vector, d can be written as dr ar. And let the Gaussian surface is a sphere of radius r, which is enclosing charge q. So for Gaussian surface, that is the surface of radius r, this ds is normal to ar. ds, which is normal to ar, is given by ds is equals to r square sine theta d phi ar. This formula also we have seen in the previous derivation. Then you use this d dot ds is equals to, we will get, in place of d we can write dr ar. So when you put dr ar dot ar becomes 1, and here we get the formula dr r square sine theta d phi. Now if we do the integration both the side, here it becomes integration of d dot ds. This side again we have theta angle and phi angle. So in the integration sign we can put the limit of 0 to 2 pi and 0 to pi. Then we simplify it and we get 4 pi r square dr. So we got integration of d dot ds is equals to 4 pi r square dr. But we already know that integration of d dot ds is equals to q. So we can equate this, and because these two terms are same, we get q is equals to 4 pi r square dr. You further simplify it, you get dr is equals to q upon 4 pi r square, and this can be written as d is equals to, we already have written this formula, d is equals to dr ar. So dr is equals to q upon 4 pi r square. You put here, you get d is equals to q upon 4 pi r square ar, and as we know that d is equals to epsilon naught e. So E is equals to, we get d upon epsilon naught. So we can put the value of d here, it becomes q upon 4 pi epsilon naught r square ar, which is the formula of electric field intensity due to point charge. So here we have obtained flux density and field intensity by using Gauss law. Let's move to next topic. We can find field intensity due to infinite length line charge by using Gauss law. Here also we have to consider one Gaussian surface. And whenever we have to use line charge, we consider cylindrical system, right? So we are considering an infinite length line charge of line charge density rho L coulomb per meter, and it is lying on z axis. Here in this diagram you can see it is lying on z axis, and z axis is extending from minus infinity to plus infinity. So we have considered a cylinder. Now you consider the Gaussian surface as right circular cylindrical with z axis as its axis, okay, and radius r as this, right, and the length of the cylinder, this length is given by L. Next, so the flux density at any point on the surface is directed radially outward. In this portion you can see, okay, and the unit vector is given by again AR, right. So the flux density at any point on surface is directed radially outward, that is in AR direction according to cylindrical coordinate system. Now let's consider a differential surface area ds here. This is this differential surface area, right, and it is at a radial distance r from the line charge, and this line charge we have considered it is lying on z axis, right. So the direction normal to ds is this AR, okay. Now as the line charge is along z axis, there cannot be any component of d in z direction, okay. So d will be only having radial components, right. How? We will see. So we already know q is equals to integration of d dot ds. This integration has to be evaluated for side surface, top surface and bottom surface. Side surface means this is top surface and this one is bottom surface. So we will elaborate it and we will write this formula as q is equals to integration of d dot ds for side plus integration of d dot ds for top and integration of d dot ds for bottom, okay. And d is equals to, again it is because radially outward, so it can be written as dr ar, okay, and ds is equals to r d phi dz ar, the area of this particular surface, and again the direction will be normal to the ar, right. So we put these d and ds in the formula, we get d dot ds is equals to drr d phi dz ar dot ar, again ar dot ar becomes 1, and we get drr d phi dz. Okay, this dr is constant over the side surface, and as d has only radial components, there will be no component in plus z and minus z direction, means az and minus az. So integration will be over the top and bottom surface will be equals to 0. So that is how we write integration of d dot ds for top and bottom is equals to 0. So we have in this formula these two are gone, and now we have only q is equals to integration of d dot ds for side, and already we have got this formula. By putting the value of d and ds, we get integration of side dr r d phi dz. So now here integration is with respect to phi and z. So the limit of z is equals to 0 to L, or it can be taken as minus infinity to infinity, but here for our cylinder the length of cylinder is L, so it can be taken as 0 to L, and phi as usual its limit is 0 to 2 pi, and remaining formula will be same dr r d phi dz. So when we integrate it, when we simplify it, we get q is equals to 2 pi r drl. dr is q upon 2 pi rl, okay, and d is equals to dr ar. We put the value of dr into this formula and we get q upon 2 pi rl ar, okay. And as we know, the line charge density is charge per unit length. So q by L is equals to rho L coulomb per meter, and d is equals to, we can put in place of q by L, we can put rho L. So this formula becomes rho L upon 2 pi r ar, and the unit is coulomb per meter square. And as we know, d is equals to epsilon naught E. So E is equals to d upon epsilon naught. So again we put the value of d into this formula and it becomes rho L upon 2 pi epsilon naught r ar volt per meter. So by using Gauss law, here we have got field intensity and flux density due to infinite length line charge. So thank you very much. In case of any query, you can write to us. Thank you very much once again.